You've got to be clear here that efficiency and unbiasedness are two separate sets. When you combine them together, then Gas-Markov theorem claims that the least square method is the best possible available alternative. So, you've got to be clear about this adjective that we use: least, linear, I don't know, square, and so on. So you've got to kind of like understand these things to be able to express them in terms of condition 1, 2, 3, 4, 5, but also in terms of, okay, what do you mean by least? To be able to explain it. And by the way, some of you are in the habit of writing page and a half for an answer. You're not going to get any more by writing over and over again, okay? Please be precise. Typically, the questions I ask, one short, clear English sentence. Sentence in English should be adequate to answer it, okay? And if I'm asking you a question, don't say everything we've learned and know about that topic. Focus your answer, direct that answer to the specific question you answer. Okay? So I'm asking something about first order serial correlation. Don't tell me everything you know about serial correlation. Just say first order serial correlation means that the a variable is correlated with its own lag value one period before, but not any period beyond that. Okay. So that's the beginning. And the conditions, most of the time we cover this course in the context of cross-section data. So Gas-Markov theory, unless I tell you otherwise, refers to the conditions required for blue least square estimates in the context of cross-section. Except when we get to sort of further down there. Do you have that one page that I give you guys, please? Okay. So this is the first row here. Right. Next. We also looked a lot at misspecification. I actually spent a lot of energy telling you about misspecification because it really is probably the single most important econometric problem. It's certainly the single most important issue referred to as unbiased estimate. Every time you have an important variable, relevant variable, missing from your model, it will be sitting in the error table. More often than not, that missing variable is correlated with some of the variables you retain in your equation, which means that on the account of that correlation, your residual and your variables are correlated. If that variable is correlated, you are violating the key assumption of the classical model. So we call it x1, x2, and y. So x1 and x2 are correlated. Typically, we always think of age and education, maybe gender and education. Maybe men tend to be less bothered about education, enter the job market earlier. Women tend to be more focused on obtaining higher level education and so on. There is some empirical evidence for that. So if the two are correlated, then this becomes part of your error term. And the new error term will therefore be correlated with your X. Then the estimates will be biased. And as I tried to explain to you, it will be biased not in the sense of affecting the coefficient estimate at next one, it will affect the coefficient values, estimates of everything in the model, everything. It contaminates the whole lot. It's a big issue. So here is the assumption number 2. What happens if they're correlated? What happens say mu star is correlated with x1.
Your conventional mean.
This is different from any possible correlation between x2 and x1 and x2, which is not correlated with this one. So for example, if you didn't leave any important explanatory variable out of the equation, you will have correlation between your x1 and x2. But you won't affect the biasness. You just have collinearity, maybe high degree of collinearity. But it is not correlated in any way with the residual of the error. Okay, so you've got to understand that was not very evident in your first midterm exam results. Many students mix up the correlation between the variables with the correlation between the variables and the error term. It is the second one which is a major problem. The first one is not a big deal. You know, typically every time you run a regression, to some extent, some of your variables are going to be correlated. And as we learn, unless multicollinearity is perfect, high multicollinearity does not affect the unbiasedness of the estimates. So you've got to understand very clearly the difference, okay? The difference between correlation between your variables among themselves and the correlation between the residual and the variables, especially if you leave out an important relevant variable out of the equation. Okay, so I expect you to sort of be clear and distinguish between these two cases. So, you know, you've given some information about your x and y are correlated, and then that might affect the coefficient values you get from each one of them. Is it biased? Are those coefficient values biased? No. But if x and y are correlated, and sorry, if x1 and x2 are correlated, and x2 is an important explanatory variable left out of the equation, are your residual and x1 correlated? Most certainly. Okay. Then sometimes you could, you know, some of the questions come from my lecture notes. So have a look at those lecture notes. They are typically short, they're between 5 to 10 pages, and there aren't very many of them. But you could actually work out the extent of the bias. If it is biased, is it biased upward or downward? And what I said was, for example, if x1 and x2 are correlated, it's very simple. You run x2 and x1 because they're correlated, right? So and you substitute into the equation. You're going to get a compound parameter, partly the result of the original parameter, partly the result of these ones. And then you can always say, okay, well, I expect this to be positive or negative or whatever, the work out what the product is going to be, and say, okay, on those bases, the model is over or underestimated. Okay? Yes?
So then basically then you're saying that you're going to regress x2 on x1 and then see it's the coefficient.
No, if you leave x2 out and x2 is important, the estimate of bias, okay? You agree on that, right?
Yeah.
I could, you know, you could address the question by taking it a step further. Is it biased upward or downwards? And the way to answer that is, well, if the two are correlated, it means there is some relationship between x1 and x2 of that nature, okay? In other words, beta 1 is unlikely to be 0. So you substitute on that, and you work out the value of the coefficient of x1, how much it changes. Then you look at the what you expected sign for each of the variables, and by arguing through, you could say, okay, well, these variables are both likely to be positive, or both negative, or one negative, one positive, and so on. So you take all these things into account. That will tell you if you're upwardly or downwardly. In this simple case, it's often actually in real applied econometric work, it's not so easy to predict the outcome because there may be 2 or 3 variables, and it is not straightforward to argue on the basis of the expected direction of effect what sign, whether it's going to be moving upward or downwards. You may just have to be happy by saying that it is biased, and we have that.
So then that's like the problem set we had with the open heart surgery thing and the eating or whatever it was.
Yeah, for example, that would be an example of it. Yeah, I mean, is that there are many other. I'm not going to give you a question that you haven't done a problem set or a quiz or is not in my lecture notes, or it wasn't covered one way or the other. At least not the same question, but the same type of question in the previous exam. I just want you to develop a relatively non-mathematical, but nonetheless logical, analytical sense of what exactly is misspecification. It is a major problem. And especially because we didn't really get in this course to tell you what the solution for misspecification is. I gave you some sort of solutions, like you put it in and out of the equation, suddenly the t ratios on the variable keeps jumping up and down, but the proper solution requires you to learn about instrumental variable, which we unfortunately haven't had time to cover. Okay, so next. Then we look at misspecification from two different angles, remember guys, okay? We looked at misspecification if inclusion of a relevant variable or exclusion of an irrelevant variable, inclusion of an irrelevant variable or exclusion of a relevant variable, the consequences of it, and so on. Remember, inclusion of an irrelevant variable. If a variable is irrelevant, first of all, it's unlikely to have a significant impact, and a high T ratio on the variable is irrelevant after. The only thing is that that variable might be correlated with other variables, which it affects a little bit, typically, the standard errors. But more often than not, the other one, exclusion of a relevant variable, that's a major problem. Okay? And many times, not just in this context, many other times, we're looking at having a chat with different people. In last class about panel data, and I was saying that panel data can control for the effect of exclusion of irrelevant variable if they don't change across time, or we have no data for it. That's one of the most powerful aspects of panel data. But if you approach me after the class, I'll tell you why panel data can do that, but time series and cross-section cannot. But we're constantly having to deal with this problem. What's really, even the model that we think is good, there's always something you could think of that is not there, that is potentially likely to make your estimates biased because it's sitting inside your head. So, clear understanding. And the other thing I said was misspecification when you fit the wrong function. Okay, so that would be an example. Say, the relationship between earning and age is quadratic. But we leave the quadratic term out. That's exactly like leaving x2 out. Because x squared and x are correlated. You leave the quadratic term out. By mistake, you fit a linear regression to the equation, and the estimate you're going to obtain from age is biased. The intercept will also be biased because you fit the wrong functional form, not because you left out any important variable. Age is there. The only problem is that age does not enter the equation linearly, but it enters the equation quadratically. If you make that mistake, and quadratic term is statistically significant, that's like saying fitting a relationship between two variables with the wrong functional form. That also generates biased estimates. Then I also looked, when we were looking at this example here, so about nonlinearities in this context, and remember what we mean by by saying that OLS requires the model to be linear. What exactly do we mean, guys? Class, what do we mean by OLS model should be linear? Anyone? Yes?
Not be exponential.
In what? Yes.
The line of best fit has to be linear in the data, so the data must be linear as well.
What do we mean by the model must be linear? Any suggestion? Yes.
I mean, like, technically, you can always like, take the log of something and then make it linear. So, I mean, as long as you can transform the given equation to like a linearized, yeah, as long as I guess.
Well, once you linearize it, then the model is linear. So,
yeah, so you just
more or less is yeah. But what kind of thing? Well, that's when we can deal with the nonlinear models come. What if we can't? Remember what we did in the last final time series class, where we had to estimate the equation nonlinearly because it's no longer possible by means of taking log and so on, convert it into linear. What happened there? Why was it that we couldn't just do what one of my students here suggested, just linearizing it by taking the log? When we say OLS condition means that it should be linear, we mean that it should be linear in parameter, not variables. Okay? If an equation contains a parameter like beta squared, or beta 0 multiplied by beta 1, or beta 1 divided by beta 0, or beta 0, the exponential of beta 0, then that model is not linear in parameter. That cannot be estimated by OLS. That violates the very first step, the very first conditions of OLS. So when you look at the models, different models, you look at it, if it's like the equation that we estimated by quasi-difference, I'm going to talk about it in a minute, quasi-difference correction for serial correlation, the Ray's method. And it turns out that the parameters of the serially uncorrelated equation is nonlinear, meaning that it's a multiplication of different parameters. And that model is nonlinear. Even if it is linear in variables, it is nonlinear. It cannot be estimated by least square regression. You can't fit a straight line to it. So be careful. Look at the different type of functional forms in front of you and see if it is simply like, for example, Cobb-Douglas production function, right? Cobb-Douglas production function, it's something like that. Your output is a function of your capital and your labor. This model can be linearized. You take the total output and you have the product becomes the sum of squares. You take the log of that, the beta comes in front of you, log of k, gamma comes in front of L, log of L. Then you apply OLS. Because alpha, gamma, and beta are not just linear coefficients, just like before. Okay, so I get constant time signal. Okay. It would be a different thing if you had an equation in which, say, output was the function of And this one wouldn't be linear. Because the coefficients, the parameters are not linear. Okay? Even if these are products and you linearize it, say you were writing it as a product of 3 terms, you linearize it so that you could write it as sum of logarithmic terms, you still have in front of it beta squared in front of log of k, or you still have in front of log of label beta divided by gamma. So you've got to understand the difference between linearity, non-linearity in variables and non-linearity in parameters. It is the non-linearity in parameters that violates the OLS condition. We looked at perfect heteroscedasticity, and I told you, as long as it's not perfect, as long as we don't fall into dummy variable trap, as long as we leave one category out as a reference, then multicollinearity, it does not undermine the unbiased estimates if your model is otherwise correctly specified. So that goes up to the middle of the page. Then we have those 4 or 5 conditions for the unbiasedness of the estimates are fulfilled. Now, as I said, you have one unbiased estimate, you may have many unbiased estimates. So if your estimates are large, obtained from this distribution, they may also be obtained from this distribution. The second one obviously has a much larger variations around the mean compared to the first. That's what we mean by least square being less. The one that least square obtained is also is unbiased, but it has a small amount of variation. Otherwise, in other words, the mean value here is obtained by averaging over these observations that are not very far from the mean. Whereas mean value here is obtained from observations, some of which are very far from the mean, mainly standard deviation away from the mean. Okay, so heteroscedasticity. You generally have heteroscedasticity if the residual, not the variable itself, the residual of the standard errors, if you like, of your explanatory variable is correlated with your standard errors of the error term. Not that the variables themselves, their residuals, the precision with which they are estimated seems to be changing together. Okay. So how do we test for it? Well, we learned about 2 different tests. We learned about the white test, and we learned about the pagan test. What's the pagan test, guys? What's the white test? Pagan test? Supposing this is your regression,
running residual sum of squares from the model and all the independent variables in the model.
sorry? Say that. Yeah.
You run the residual sum of squares from the model on each independent variable.
So what you do is you run this regression, because the whole point is that is the residual variance keeps changing with any of these variables. So you obtain the run the equation, obtain its squared value. Let's call it for each observation. Then you regress it on all your explanatory variables. unless you know which particular explanatory variable is correlated, which you don't know. And the assumption in Hagen and White test is that it could potentially be correlated with all the variables, or with just one of them, or two of them, but not three, and so on. So, on those based on that rationale, they run it on all explanatory variables. Okay.
It won't tell you which one has correlation, it'll tell you if there's correlation, because you're writing it.
Yeah. So the idea is that then think of it that way, and I want you to be clear about it. What exactly are we testing here? What's the null hypothesis? What's the null hypothesis, guys, here? If you were to write it, how do you write it? Stamped in.
Beta 1 equals beta 2, and
At least we'll have half the screen. Sorry? Let's see if I fold it the other way around.
Can we just,
Pull it down. No, you can't do it.
bust it?
The spring is gone. The spring is gone. You see, you broke it? Okay, let's do it like that. They say necessity is the mother of invention. Right. So, what's the null hypothesis here, guys? Anyone? What exactly are we testing?
I'm sorry.
Yes.
Beta 1 equal, beta 0 equal beta 1, 2 equals 0.
Exactly. We're testing whether this is correlated with one or more of these things. If it's not correlated, then your null is that beta 1 and beta 2 are equal to 0. So the alternative hypothesis is therefore beta 1 and beta 2 are not 0. At least one of them is correlated with this. So, how do we test it? I told you about the Lagrange multiplier test, which is somewhat simpler than the F test. You obtain the R square of this equation, not R square of the original equation, of this one. Okay? Let's call it R square of E for the residual. Then Lagrange multiplier test is the result of multiplying your sample size by your R square of the residual equation. Okay. You can show that this statistic has a chi-square distribution. With the degree of freedom being equal to the number of restrictions you're imposing. In this case, 2. Degree of freedom is 2. And therefore, you go to the chi-square table. Any textbook here? Yeah, thank you. You go to the chi-square table. You decide on a level of confidence at which you wish to test, 1%, 5%, or 10%. Let's say the most standard is to go for 1%. So the degree of freedom, i.e. the number of restrictions for a chi-square test is here. Okay, that's your degree of freedom. Here, the number of restrictions. And then up here, there are 3 columns, 1%, 5%, or 10%. just go in front of, say, for example, 3, we've got testing 3 restriction, maybe the intercept included. Then you go here in front of 3, and the critical value is something like 6.25. So that's your critical value. Then you test your Lagrange multiplier test statistics against that critical value. If it is higher, you reject the null hypothesis that they have no effect on the residual receipt, i.e. you have heteroscedasticity.
But if the what is higher?
Sorry?
If the what is higher?
You're happy about how to obtain the Lagrange multiplier statistics, right?
Okay.
You understand. Well, like F-test, like T-test, you need a critical value from the table to compare it with, to decide whether or not you should reject. So what I'm saying is that's how you find your critical value. So I expect you to be able to work with this table. Okay? And the critical value depends on the number of restrictions that you learn from your null hypothesis. That's the restrictions you impose. Then decide 95%, I'm testing at 95%, and find the critical value. Then compare that critical value with with your test statistics. If your test statistics exceeds the critical value, you reject the null hypothesis that the coefficient of the explanatory variable have no impact on the residual, i.e. you have heteroscedasticity. Okay. So it's very simple. And later when you start working with nonlinear estimation, you find that more than F and T distribution, chi-square distribution fits and is very useful and often employed when you're dealing with nonlinear estimation, when you're testing the nonlinear estimation. Chi-square distribution. Lagrange multiplier, if you get that residual and multiply it by the sample size, by the way, it's not the adjusted residual, it's the unadjusted residual. Multiplied by the sample size, that combination can be shown to have a chi-square distribution. So you're actually testing with reference to the critical value in a chi-square table. And the next step is, how do we correct for it? And I told you a number of different things. One general, very appealing method is if you don't know the form of heteroscedasticity. And if you don't know the form of heteroscedasticity, then the best thing is to go for the wide heteroscedasticity robust standard errors. It is robust. It doesn't correct for heteroscedasticity, but if you don't have heteroscedasticity, if your standard errors are homoescedastic, it also produces the standard OLS homoescedastic standard errors. If it is, then it gives you correct the standard errors so as to be immune to the presence of heteroscedasticity in your data. It takes that into account when it works out the value for your. How it does that? It's actually in the formula according to which it does that correction. It's in my lecture notes. I'm not gonna ask you a question to reproduce that formula, okay? But if you're interested, it's in my lecture notes. It tells you how the white test actually corrects for what's the basis of robust standard errors. It corrects for the incorrect or biased standard errors. So what else? The other thing I said, and we did quite a bit of exercise on that as well, was if we knew the form of heteroscedasticity. For example, we know that heteroscedasticity is related to x2, but not to x1. Now, the key assumption of OLS, guys, what's the assumption of heteroscedasticity, homoescedasticity? Who can tell me what homoescedasticity is?
Constant variance?
Sorry?
Constant variance?
Constant variance, okay? If the variance of the error term is correlated with variance of your explanatory variables and the explanatory variables change, then it's no longer going to be constant. Right? So typically, you will have the standard errors for your variable, which is the initial non-changing one, but it keeps changing with one of your standard variables. So typically, let's call that it keeps changing the, let's call it H, give it a German name. You could call that, if you like, heteroscedasticity function. So if you're correcting for if you're correcting for the residual standard errors, then this is the variance. So the square root of the variance is going to be your standard errors or standard deviation. So you're basically, you want the standard errors, that is the original, plus some square root of your heteroelasticity function. Then you pay attention to the form of the heteroscedasticity that is suggested to you. If the form of heteroscedasticity is that this is changing with x2, then what's the square root of hi in this case, guys?
Theta square root of x.
Sorry?
Theta square root of x2.
It is the square root of x. If on the other hand, it tells you that the form of heteroscedasticity is that it changes with the squared value of x2, then what's the square root of h1?
X2.
It's just x. Okay? So just because they put the just because in the process of transferring the variance into standard errors we take root of the square root of the heteroscedasticity function, you mustn't be confused that that always means that you take the square root of the thing. You just look what information you have about the functional form between the variable and the standard error. So in this case, it's just x as you said. So the square root of hi is just x itself, rather x2. So, yes?
Yeah, can you say that again? So you said that to correct for the heteros, whatever that thing is. You have to do the standard error times the square root of the estimate.
Yeah, I mean you're clear about standard errors, standard deviation being a square root of the variance, right? So if you're correcting for the standard errors, you just take the square root of that, right?
And then that's all I could say. Like, on the
No,
test,
I mean
and I'm good.
basically what I'm saying is that when you do that, you are taking the square root of the constant variance, but you're also taking the square root of the variable with which it's changing.
Okay.
And that variable, then you have to be alert and pay attention to the form of the functional form that, if the functional form is square, is linear, is logarithmic, whatever, then it is that which goes under the square root. In the simplest case, for example, when it is quadratic, then you end up with a linear term. If it's more complicated, like the logarithmic, then you have the square root of the logarithm of the variable. But then you learn that, okay, say it's linear, then your non-constant variance is going to look like let's say it is working out what with the log of x, and in order to get rid of it, you have to divide by the inverse value of that, right? So, say in this case, one solution to get rid of heteroscedasticity is to divide it by the inverse so that they cancel out. But you can't just do it for the residual, can you? You have to, in order to change the estimate, the right and the left hand side of the estimate function, you divide the entire equation. As you do that, then you no longer have these variables, the coefficients are no longer this, it's going to change, it becomes something else. It's an example of what we call generalized least square method, and which is an alternative in this case. Only the particular version that you apply. Generalized least square is when you take a simple linear model, you transfer it in order to get rid of heteroscedasticity or serial correlation, but in the process you generate another nonlinear equation. And it's generalized because it's no longer, you can apply OLS in a more general context. Okay. So in this case, if you then correct for heteroscedasticity by using the weight for each of the variables, dividing it by 1 over x. So if you've got these equations, say, for example, the variable there was in logarithmic terms, x2, then you divide the whole equation by, say, square root of x2, everything, square root of x2, and so on, square root of x2, and then finally the residual will be divided by the square root of x2. That gives you a constant, that gets rid of the changing component of it. I mean, you've corrected the equation so as to result in a constant variance. And therefore, so that's what we do in here. Okay? This part. So heteroscedasticity, when the variable is, the variance of the residual is correlated with the variance of one or more of the exponential variable. But how do you test it? Hagen or White test. How do you correct for it? Well, if you don't know the form of heteroscedasticity, you apply the robust method. If you do know the form of heteroscedasticity, for example, you could apply generalized least square, and a particular version of it is what we call a weighted least square, where you weigh by the inverse of the square root of the variable suspected of causing heteroscedasticity. Okay, so this is so far in the context of this is so far in the context of the heteroscedasticity in the context of cross-sectional. Then we looked at other cross-sectional model where the model wasn't necessarily linear, or if it was linear, it's kind of like a bit awkward and uncomfortable. And in that context, we looked at the role of the dummy variable. Okay, we did an extensive set of exercises to tell you the difference between the intercept and the slope dummy variable. What's the difference, guys? Intercept and slope dummies?
Intercept dummy variable will change the intercept along the line, and the slope dummy variable will just change the slope. So
How do you put that into the equation? Yes.
So you use variable 0 and 1, or you use 0 and 1 to represent if it is present or if it's not. And when it's 0, it's not going to change the intercept or slope, I guess, too, technically. And when it's 1, it'll change either just the slope or the slope and the intercept.
if you want to,
I'm sorry, just the intercept or.
Good, but I want a little bit more specific. You kind of have a sense of.
you just have the
but
dummy
you don't
variable as its own parameter for the slope.
So, like, you want me to use, like, examples?
No.
Like, if you use female as 0 and then male is 1, And if they're not female, then you put 0 to start the chain.
Let's say you're looking at impact of education on learning. You have something called race. And this race is a dummy which is 1 if, let's say, African American and 0 otherwise, Asian, say Hispanic. So if you're dummy, I'm going to actually change that so that you have a more graphic. Let's call it BR. If you're dummy, if the individual is not an African American, then the dummy has a value of 0, right? So this term drops out. Your equation is like this. If the individual is African American, then BR becomes 1 plus the residual. In other words, 1 is 1. When you multiply alpha 2 by 1, you're just going to get alpha 2. Since alpha 2 is not correlated with any of the explanatory variables, you can rewrite this equation as having an intercept of alpha 0 plus alpha t plus alpha 1 and say years of education. So the difference between the two groups is, in one case, the intercept is alpha 0. In the other case, for African American, the intercept is alpha 0 plus alpha 2. Everything else, in particular, they estimate before the x2 remains unchanged. This doesn't change, these two don't change. So the slope of the curve is the same. That's the point that one of my students was making earlier. But the intercept is, in other words, you're going to have two parallel lines. The intercept is going to be different, but the slope is going to be the same. It's a different thing if you allow for this change. We don't complain very much because this is our last class. We were lucky it didn't break early. So, now look what happens if you allow the dummy to interact with the variable for years of education. And you have y is alpha 0 plus alpha 1 for, say, years of education, plus dummy alpha 2 dummy plus a new variable with alpha 3 which is your years of education multiplied by the dummy plus the residual. Again, to see what impact it has, enter 0 and 1 as values to the dummy and see what happens. If it's 0, if D is 0, then that term drops out, and this term drops out. So your equation will be on the other hand, if your earner is an African American and dummy takes the value of 1, then your equation is going to be
the full model.
just like before. This is going to be 1, so intercept is going to be different. Alpha 0 plus alpha 2. But now you have 2x variable with x. This has x in it and this has x in it. So give the value of 1 to this. You have alpha 1x and alpha 3x. You factorize, so you have alpha 1 plus alpha 3x plus the residual. So, compare the two equations. If dummy is 0, you have this. If dummy is 1, the intercept has changed, but now the coefficient before x, i.e. the slope, has also changed. Here is alpha 1, here is alpha 1 plus alpha 3. That means that your equation is more likely to look something like this. So the intercept is different, but the slope is also different. This one is flat, for example, the other one is steep. They're no longer parallel. That's the difference between the. Of course, if you make it more complicated by saying, I don't want the dummy to enter separately, but only interactively, then you have a situation in which the initial point is the same for both equations, but one of them has a different intercept compared to the other. But they have the same slope because of the absence of the dummy variable entering the equation separately on its own.
Isn't that the same intercept but different slope?
If you remove the d1 from the equation, so you have x plus an interactive term with the dummy, but no dummy term on its own, then only the intercept will change. Only the slope will change. The intercept will remain as it is before. Okay? So I expect you to understand, as I said, we did a lot of exercise on that, the difference between intercept and given an equation, the difference between intercept dummy and slope dummy. What else did we do that is worth mentioning? Yeah, we did again. Within the same context, chapter 7, we looked at the linear probability model. Just be aware that the linear probability model coefficient estimate is for the probability of your dependent variable. If you have a dependent variable which has a value of 0 to 1, the probability of your dependent variable taking the value of 1, i.e. what's the probability of getting a success, quote unquote. Okay? So you say, okay, my coefficient values, if it's in percentages, means that 1% increase in your GPA increases the probability of being admitted for a graduate program by so much. That's the meaning of the coefficient estimate. If you define probability of admit as being equal to 1 for your admission indicator, and as being equal to 0 otherwise, if you reject. Okay, the other thing we did several times was to obtain a better measure of goodness of fit for linear probability model, because linear probability models normally have an extremely poor measure of goodness of fit, because basically you only have two types of variations in the data. say if this is 1 and this is 0, the observations are going to be on these things. So when you fit a line, that line is obtained with a relatively little variations of your dependent variable. So the alternative I suggested was to work out a way of obtaining a measure of goodness of fit based on percentage of time that your model correctly predicts the estimated probability for your dependent variable. So if you have, say, you're looking at the probability of being accepted and your dependent variable in the model is 0 and 1, you estimate that model, you're going to get a range of probabilities. If it is linear probability model, sometimes if you're unlucky, values which fall outside the 0 and 1. But generally, most of them are going to be between 0 and 1. You can't really compare them with the actual outcome because actual outcome is also 0 and 1. So the way to do it is to convert the observation, the predicted observation also into 0 and 1 and then compare them. I suggested that you take a relatively neutral probability values like 0.05 and divide the predicted outcome of your dependent variable into two groups. Those anything above 0.05, we call it high probability of success and give it a value of 1. Anything below that, we call it low probability of success, give it a value of 0. Then you have two types of 0 and 1 variable. One from the actual model and one from the predicted model. You compare them. You look at the difference from the actual and predicted. So it will be 1 and 0, and this one can also be 1 and 0. If it is both of them are 1 or both of them 0, the difference between them is going to be 0. That means those are the cases where the model has correctly predicted the outcome. If on the other hand, actual is 1 and your model predicted 0, then the difference is going to be 1. And it's not a correct one. If the actual value was 1 and the predicted was 0 and the predicted was 1, then the difference is going to be -1. That's also not correct outcome. Then you simply get the computer to count the number of cases which falls into these categories. And you divide the number of correctly predicted outcome from your model by the total number of observations. That will give you the percentage of time that the model has correctly predicted the outcome. That would be an alternative measure of goodness of fit to your model. So that is for linear probability model. And now we also looked at within the chapter 7, we looked at how to conduct a Charles structural break test. Charles structural break test, you're not testing the joint restriction between a pre or subgroup of your parameters. You are actually checking whether the entire set of parameters would look different if you divide your samples into two samples on the basis of either a time series or a cross-sectional criteria. In the cross, we looked at the cross-sectional criteria. We looked at it at, say, between, man and woman in the sample who are earners. And you say, I don't believe the coefficient impact of education on earning is the same for men as it is for women. So you divide the sample into two groups. You first obtain the residual sum of the square for the entire sample. Then you allow the impact of education on earning to be different by running two separate samples. One for a group consisting solely of male workers, one for the group consisting solely of female workers. In each of these three cases, obtain the residual sum of errors. The unrestricted residual sum of errors are the ones that you obtain for your smaller subsamples. The restricted one, you are forcing that the two groups in the sample to have the same value or the same impact of education on their earning. Then you put it into the formula. And I expect you to know that formula. Okay, so is the pooled residual sum of the squares minus the sum of the two subsamples divided by the number of restriction, which is the total number of parameters in the equation.
Can you write the formula on the board actually, yeah?
It's in my
Notes.
in my lecture notes. Yeah, it's like this.
And it's called what again? Charles structure break test? Chow?
Structure break test. Okay, so I expect you, and then you run that, you obtain your FS statistics, then you go to the F table. Quiet, please. If you want to be you run your FS statistics. You remember how to use the F table. You need 2 degrees of freedom, denominator and numerator, to use the F table. Can I just have your book again, please? I'm sorry to be you did the F test for the previous exam, so you should know how to deal with it. But this is the F table. Okay. So you have the numerator, degrees of freedom, and denominator, degrees of freedom. And you go inside the cell, you find the critical values. Just like the chi-square test, you compare the critical value with your F statistic. If it's greater, you reject the hypothesis. Now, that's the chi-square value. It's something like this. You have the residual sum for the pool data minus the residual sum of the square for each of the subsamples divided by the number of restrictions. And yeah, you were asking for it. You have to go to my note to see. This is the residual sum of the square you obtain for the entire equation. These are the 2 residuals you obtain for each of the subsamples. You take this sum away from that, divided by the number of restrictions, which is the total number of parameters in the equation. And then the denominator is the unrestricted one, which is the sum of these 2, divided by sample size, because you run the same equation twice. The number of parameters is twice as many, so 2 cubes.
So is it only 2, for example, like the 2, so R1 and R2, right? So in the F test previously for cross series, it was Q with the number of restrictions.
Yeah, here the number of restrictions,
The same as
yeah, here the number of restrictions in the entire parameter set, because you're saying the entire equation would look different if I run it for male compared to B. Or that the entire equation would look different if I run it before 1960 and after 1960. Okay, so if they're different, then when you run for the entire session, you are you're restricting the parameter values to be the same. So they're twice as many. So one final thing that we did was to look at time series, and there I expect you to know how the key assumptions of OLS are modified. For example, independence of the residual from the explanatory variable. Then you have to discuss various type of exogeneity and so on. And since in a time series you have lag values, it opens up 2 types of independence. Independence where the residual and your explanatory variables are not correlated in the current period, and independence where the 2 are uncorrelated, not just in the current period, but also the residual is uncorrelated with all the past lag values of your dependent variables. Obviously, the second one is a much stronger assumptions of independence. We call it strict exogeneity, but you should know that. And finally, the last part of the residual is when you're talking, when you have serial correlation. Serial correlation is like heterostochasticity. It does not affect the unbiasedness of your estimate, only affects the the T ratios and so on. But the essence of serial correlation is what, guys? What under what circumstances you have serial correlation?
It's when like the error terms are correlated.
When the error terms is correlated with its own lag value, one or more period. Typically, most of the time we focus on the cases when error term is correlated only with its previous value. We call that error term of the first order. And the way to look at it, that's very simple, but you should have a good mental image of it. Is this. You have a simple equation like this. You have a simple equation like but your error term is correlated, which means that if you run your error term on its own lag value, and this coefficient here is bound to be significant if they're correlated, right? If the two move together, then regressing one on the other is bound to be significant. If it moves only with the first gap and not beyond that, and you have, this is an example of an autoregressive model of first order. Autoregressive model of the first order can be applied, not just the first order, autoregressive models can be applied to any variable time series variable, not just to the error term. Every time you model the behavior of a variable based on its own value in the past, you are running an autoregressive. In this case, we are doing an autoregressive. Therefore, if you're testing for serial correlation, you are in fact testing whether your null hypothesis, which is the variable rho here, is equal to 0 against the alternative hypothesis that it is different. And I suggested that a simple way of doing it is precisely to do that regression. Do the regression, obtain the residual, then regress that residual on its own lag value, and look at the T ratio coefficient estimates that you obtain on the lag value. If that T ratio is significant, that provides you an elementary evidence that you have serial correlation, which means that your residual are tailing one another. The consequence of serial correlation, just as the consequence of heteroscedasticity, if you have it, does not affect the unbiasedness of your estimate if the model is correctly specified. It only affects the standard errors, which means that when you divide the parameter estimate by the standard errors, the T ratios can be misleading, F test can be misleading, chi-square test can be misleading. Basically, testing becomes a problem.
Yeah, that's
Okay, so what we did was pay attention here. The solution is very, very interesting. If this is serially correlated, then you run the regression. This one is a classical error. It's not serially correlated. Mu is not correlated with its own lag value, but this one is. So what you want to do, the solution consists of transferring the original equation, and some are getting it, re-estimate this equation with this residual rather than the. And the way I suggested to do it was, if you lag this, okay, you do it in 2 steps or 3 steps. 3 steps. 1. Lag bar 1 period. 2. Multiply both sides by 4 regressive coefficient. 3. Take the difference between the two equations. This one. When you do that, what's going to happen is that in the second equation, after you multiply it and lag it one period, you're going to get this difference. It's going to be like that. And we know that difference is equal to a serially uncorrelated error tail. Okay, I repeat. You lag the equation one period, multiply both sides of it by the autocorrelation coefficient, and then take the difference of the right and the left-hand side from the original equation. When you do that, basically what you're doing, you're taking advantage of this information here. You are replacing the equation serially correlated with this serially uncorrelated equation. Then I suggested, and that is the version of the generalized least square that is employed by the Kray's method. Again, when you do that, the code is going to result in a model which is nonlinear in parameter. It is no longer just alpha 1, it's going to be some combination of alpha 1 multiplied by rho. That's a nonlinear model. It cannot be estimated by OLS. You estimate it nonlinearly, number 1. Number 2, if this model is correctly specified, then the nonlinear parameter estimates are something different than the original unbiased estimate. So in the process of correcting for standard errors, they have changed the unbiased estimate. So you must know that there is an alternative to the Kray's method. It changes, it does this, substitute this standard errors by that standard error by suitable transformation of the equation, but it retains the original OLS parameter estimates. Only changes the standard errors, because serial correlation is only a problem of the unbiased standard errors. It is not a problem of unbiased parameter estimates. Okay? So, again, by the time you do that, you're right here at the bottom. So this one page covers everything that I updated. Just keep looking at it as an example. Which was it? This page?
It's mine.
I'm gonna send you an announcement just to tell you